Alright. Howdy. Our team is Miller Boykin, Brandon Higgs, Nick Martin, and Orlando Rivera, and our project is precision target scoring. So the problem we're attempting to solve is that with just over 30 million shooters nationwide, there's no good accessible way to track performance and compete remotely. Typically, amateur shooters have to travel to shooting events across the country, costing them copious amounts of time and money. And moreover, commercial auto scoring does exist, but wireless transmission of performance data is highly limited. So our solution is to develop an affordable and portable electronic product that scores and tracks the performance of a user, collects data regarding the performance, transmits the data to an online database, and presents performance metrics on a secure, user-friendly web application. And that gives us the precision target scoring device, which is based on a laser array to detect the impact of a projectile, propagating it to a database and a web application for display. Here you can see our flow chart of the logic of the system. So it starts with the battery pack going to a 5-volt rail and a 3.3-volt rail, powering a control unit, the laser array, and some projectile detection circuitry. The projectile strikes the array, transmitting coordinates to the control unit, which propagate to the database, and then pass it on to the website for the user to view.
Howdy. Here's the power management subsystem for the PTS device. This is essentially a battery pack, and it's composed of 3 main circuits. So the first circuit right here is the charging circuit / actual batteries. The next one right here is going to be a 3.3-volt converter, and then we have a 5-volt converter at the bottom. So let's dive into the the charging circuit first. So this charging circuit is able to charge these cells with 3 amps. And it is supplied by 5 volts. So if you have a wall adapter that is converts the 120 AC to 5 volts, you're able to charge this battery pack. This pack has 16 amp hours, and that is able to, from estimations, power this device for about an hour and a half, which is the average time of a shooting session. Diving into the converters now. This 3.3-volt converter, this is responsible for powering the MCU subsystem, and the estimated current draw of that was 5 amps. This guy can do, and is tested, up to 1.5 amps. Under the ideal operating condition of 0.5 amps, this has an efficiency of 95%, and it only drops by about 0.1 volts, so it's around 3.2 volts during operation. Looking at this 5-volt converter, this is responsible for powering the laser array, the CPLD boards, and the microcontroller in the projectile detection subsystem. This guy is capable of doing up to 5 amps, and we're estimating about a 3 amp draw from all of the nominal 3 amp draw from all of the projectile detection subsystem circuits. And at that load condition, this has an efficiency of 96%. With this being said, this is it for the power management subsystem.
Howdy, my name is Brandon Higgs, and this is the projectile detection subsystem. Here you have the laser grid array. It's composed of 50 x-axis lasers and 50 y-axis lasers. Each laser is paired with a phototransistor on the opposite side of the array. For the purposes of detection, the array is split into 4 quadrants. Each quadrant has its own detection circuitry. When a projectile enters the array, it obstructs the laser beam. This causes a voltage drop at the outputs of the phototransistor board. The outputs of the phototransistors are routed to the CPLD boards via ribbon cables to a breakout board, and then ribbon cables to the CPLDs. The CPLDs have comparators configured such that when the phototransistor voltage drops below the reference voltage set by a digital potentiometer, the comparator outputs a high signal. And based on which comparator is high, the CPLD can determine the coordinates of the projectile. This information is relayed to a microcontroller via a SPI interface. The microcontroller converts these quadrant-specific coordinates to global coordinates and sends it over to the control system via a UART interface.
So the purpose of the control unit is to read in global coordinates from projectile detection Scale those global coordinates to an XY distance from the center of the target, assign a score to the shot attempt, connect to a Wi-Fi network, authenticate with Google Cloud, and establish an HTTPS connection to Firebase, and upload the scaled position and the score to the database for use by the web application. So here you can see the board for the control unit. We've got a power interface, a serial monitor, UART pins for communication, and then the ESP32 that does all the computation. This is the target that the scoring system is modeled after. This is the USPSA classic target. So according to the scoring, region A is worth 5 points, region C is worth 3, and region D is worth 1 point.
Hello, my name is Orlando Rivera, and this is the web application subsystem for the precision target scoring device. So here we can see we're on worldsgreatestshooter.web.app/login, and this is the domain name for the web application. Here you can see we have a couple of features. We have a forgotten password feature, so the user can reset their password whenever necessary. We also have a register button, so the user can create a username and they can register their birthday, their email, their password, etc. And one of the requirements as well is that when they go to create a password or even create an account for that matter, they need to meet the criteria for password strength. So we need to have at least 12 characters, an uppercase letter, a lowercase letter, a number, and a symbol, and then afterwards we'll be able to create an account. So right now I'm just going to use an existing account. So I will log into the page as of right now. And so here we can see we have a couple of widgets here that display the average score, accuracy, and the precision of the user for this recent shooting session. And we can also see some improvements within their metrics as well. Going into the stats page, now we can actually see the specifics on the scoring data as well as the projectile landing locations on the target frame. And in addition to that, we have a button for clearing the data. So if they want to clear their session data, they can do that if desired. Here we have the profile page, so the user can upload a profile image. Here we can see their email, and if they wish to change their username, they can enter their new username right here. And they can also enter in, let's say they accidentally entered their birthday incorrectly. They can also enter in their birthday as well, if need be, and update their profile respectively. And then here we have our logout feature, so we can just log out of the page and that'll send us back over to the login page for the web application.
Howdy, we're Team 25, Precision Target Scoring, and this is our final demo video. So we have the power supply off to the side. We've got a 3.3 volt rail and a 5 volt rail. That's powering our CPLD boards, our microcontroller board, and our control unit board, which will detect coordinates from this laser grid, and it will be propagated to our web application. We've got our projectile here, ready to go, and here's how it works. So you can see the coordinates are being uploaded now. And if we refresh our website, you can see that the scaled position of the hit relative to the center of the target has been added to the collection, and we have basic user metrics to track their performance over time as well.